In episode 5, we utilized principles of space-time engineering to derive the experimentally verified root mean squared charge radius of the proton, and the experimentally verified mean squared charge radius of the neutron. We derived an exact solution, common to both particles, which has never been done before. In fact, the standard model of particle physics is presently incapable of achieving this outcome. That is, the standard model of particle physics is presently incapable of using the same basic equation to describe the size of the proton and neutron simultaneously. In actuality, this is an impressive and important achievement. In this episode, we're going to take the methodology responsible for this outcome to the next level. In this episode, we'll derive the mass, energy and radii of photons and gravitons. But hang on a moment, what is a photon, and what is a graviton? Well, if we're looking at this challenge utilizing the electrogravimagnetic construct as our primary investigative tool, then to deal with gravitons, we first need to deal with photons. However, the nature of photons is not straightforward. Sometimes they behave as particles, and sometimes they behave as waves. So, what can we do about this duality? What can we do in order not to be trapped somehow? There's probably a family of possible approaches which might work, but the one we're going to use involves electrons. Why electrons? Because electrons are photon production factories. If there is any specific particle closest to the answer regarding the nature of photons, then the electron is that particle. Let's dive into it. In episode 5, we asked, what holds fundamental particles together? In the case of composite particles, such as the proton and neutron, one may wish to argue that the strong force is the only mechanism keeping composite particles together. The strong force binds quarks together, therefore, the standard model of particle physics concludes that the strong force is the only relevant mechanism. However, there's a problem with this being the only factor holding fundamental particles together. What about the electron? It has no known internal structure and is considered to be a point particle. So, what's holding it together? What stops an electron from diffusing itself into non-existence? Whatever the reason, it must act on all fundamental particles simultaneously, with varying degrees of influence. Let's begin with some basic observations. Firstly, in nature, we see that all systems seek to achieve the lowest possible energy state. Secondly, in the case of an electron, its mass energy density is significantly higher than the energy density at a radial point from the particle, at infinity. So, what prevents an electron from diffusing itself into non-existence due to the energy gradient between its center and radial infinity? Perhaps the answer to this question is that its mass energy density is in equilibrium with its spectral energy density. If so, the equilibrium point between these two forms of energy represents a boundary. A boundary that we can interpret as size. This was the hypothesis we tested, and verified, in episode 5. It is termed the zero-point field equilibrium radius. In this episode, we are not interested in the electron, not directly. We're actually more interested in the quantum vacuum, that is, the polarized zero-point field, surrounding it. Let's take a look at what we mean. In order to model the quantum vacuum surrounding an electron, we first need to describe an electron. And as everyone already knows, a defining attribute of the electron is its electric charge, typically represented as Q. However, in order to describe an electron, in the context of the quantum vacuum, we need to revisit an important discovery revealed in episode 1. We learned via Buckingham pi theory in episode 1, that electric charge evaporates in all mathematical models attempting to relate electromagnetism to gravity. Hence, Lorentz force contributions may be discarded and therefore, an electron may be modeled as a neutrally charged particle, of electron mass. These illustrations depict the curvature induced in the space-time manifold, by a neutrally charged particle of electron mass, in accordance with general relativity. The dimensions of the particle are a topic for another episode, but for now, let's simply assume that the size of an electron is defined by its zero-point field equilibrium radius, as we have done for the proton and neutron in episode 5. As you can see, the three-dimensional representation of space-time curvature is far more visually rich and complicated than its two-dimensional analog. For this reason, that is, for simplicity going forward, we will only communicate via two-dimensional representations. Please keep this in mind. At this juncture, we must emphasize and stress that the true nature of an electron is not under investigation. Only its relationship with the quantum vacuum surrounding it. So, the absence of electric charge is irrelevant with respect to the quantum vacuum, as confirmed via Buckingham pi theory in episode 1. Let's now look at what happens to the quantum vacuum in the presence of an electron. Before we can address what happens to the quantum vacuum in the presence of an electron, we need to understand the nature of the quantum vacuum ground state. That is, the quantum vacuum at its lowest possible energy level. In terms of general relativity, the quantum vacuum ground state denotes a perfectly flat space-time manifold. In other words, the quantum vacuum ground state is representative of Minkowski spacetime. The name given to this quantum vacuum condition is zero-point field. For many decades, vibrant debate has questioned whether or not the zero-point field is representative of virtual or real photons. Quantum electrodynamics favors virtual photons, whilst stochastic electrodynamics favors real photons. However, the electrogravimagnetic construct offers somewhat of a middle ground. The electrogravimagnetic concept of the zero-point field defines it to be a dark reservoir of quantum potential energy. This means that the zero-point field of flat spacetime cannot contain infinite real energy, but it does contain a vast reservoir of potential energy. This is extremely important, so please keep this in mind at all times. Because we consider the zero-point field to be a dark reservoir of quantum potential energy, it has no observable physical structure. Hence, we are required to assign a mathematical structure to it, in order to describe it. To be consistent with previous episodes, we shall describe the zero-point field as possessing the spectral characteristics of a Fourier distribution. However, in this situation, the amplitude spectrum denotes the probability of photons emerging randomly from the zero-point field. We'll discuss this in greater detail on the preceding slide, but for now, we can simply model the zero-point field by multiplying the unit harmonic operator by 0. Please refer to episode 2 for more information. In the absence of matter, that is, in a completely flat space-time manifold, the zero-point field exists as an infinitely broad spectrum of potential photon frequencies, randomly manifesting as real photons, then collapsing back into the zero-point field as quickly as they arise. This means that the harmonic cutoff mode and frequency associated with the zero-point field tends to infinity. This does not mean that an infinite quantity of real energy exists, it simply means that the zero-point field possesses the potential to release it, much like a battery. The process of energy release is random and governed by probabilities. However, it should be emphatically stressed that a truly flat space-time manifold does not and cannot physically exist. Special relativity and Minkowski spacetime are non-physical mathematical contrivances. Hence, it is statistically extremely unlikely that the zero-point field will release all of its potential energy in one catastrophic event. Let's now take a look at what happens to the quantum vacuum when we superimpose matter onto the zero-point field. In this illustration, we see the zero-point field modeled as a randomized spectrum of real photons. This is the effervescent baseline of the quantum vacuum driving the Casimir effect. But where does the energy for these wavefunctions come from? If the energy for these wavefunctions existed at the level of the zero-point field constantly, then all the energy within the zero-point field would be released in one catastrophic event. Therefore, a layer of reality must exist beneath the zero-point field where the energy for these wavefunctions must be stored. This is why we describe the zero-point field as a dark reservoir of quantum potential energy. In order for virtual photons to pop into existence, they must have been stored in some inaccessible layer of reality, as potential energy. Due to the storage layer for this quantum potential energy being physically inaccessible, we may imbue it with any structural format we wish. All logical formats are equally valid as they cannot be directly experimentally confirmed. Please do not confuse or associate this statement with the Casimir effect, which is experimentally observable. The Casimir effect occurs in the real world, but the dark reservoir of quantum potential energy fueling the Casimir effect is physically inaccessible. Therefore, it logically follows that any structural format applied to describe this dark reservoir of quantum potential energy should be efficient, in order to be consistent with all other natural phenomena. Hence, a very efficient way of storing quantum potential energy, mathematically speaking, is in accordance with a Fourier distribution. In the bottom left-hand corner of this illustration, we see the quantum potential energy associated with the zero-point field. The zero-point field is the physical manifestation of the quantum potential energy released into the physical universe when the quantum vacuum is in its ground state. We manifestly observe this process in the Casimir effect. The illustration depicts the amplitude and frequency spectra associated with the available quantum potential energy, formatted in accordance with a Fourier distribution. As described by the unit harmonic operator in episode 2, each wave function denotes a population of virtual photons and exists in conjugate pairs, as indicated and required for net zero gain. Hence the term, zero point. These wave functions mean that at any instant in time, populations of virtual photons pop into existence, but so do an equivalent population of virtual photons, 180 degrees out of phase. Consequently, no electromagnetic radiation is ever experimentally observed, mysteriously appearing from nowhere. So how do we interpret these curves? That's a good question, I'm glad you asked. The amplitude of each wave function denotes the probability of a population of photons popping into existence. As you can see, the probability of emergence into reality is significantly greater at lower frequencies than it is at higher frequencies. That is, the higher up the frequency spectrum we look, the lower the probability of virtual photons popping into existence. And as we have already established, for perfectly flat space-time geometry, the harmonic cutoff frequency tends to infinity. This also means that its probability amplitude tends to zero. In other words, it is impossible for photons of infinite frequency to exist in the physical universe. Hence, the universe cannot catastrophically collapse. When we add matter to the zero-point field, a major change occurs. The quantum vacuum becomes polarized by the presence of matter and compresses the frequency range of the zero-point field. The lower spectral frequency limit is upshifted from 0 Hz, and the upper spectral limit is downshifted from infinity. Both alternate spectral limits are mass-energy dependent. However, the structural format of the Fourier distribution is preserved. In other words, the mathematical description doesn't change, the Fourier distribution is preserved, but its lower and upper frequency limits have been modified, due to the addition of matter. We call this polarized form of the quantum vacuum, the polarizable vacuum. So how does all of this lead to the topic of gravitons? Well, if we consider any mass to be represented by a point particle, we are in fact insisting that all of its mass energy is contained in the quantum vacuum field surrounding it. Hence, if the quantum vacuum surrounding any mass can be described by a Fourier distribution, which is fully quantized, then it logically follows that a conjugate photon population pair must define the graviton. And an important question now is, what are the gravitons interacting with? How is space-time curvature generated? The answer to this will be discussed in detail on the following slide, but for now, we'll say that matter is analogous to an energy source, whilst the zero-point field is analogous to an energy sink. Let's take a closer look. So far, we have established a link between the zero-point field and the layer of inaccessible reality beneath it, termed the dark reservoir of quantum potential energy. However, if the dark reservoir of quantum potential energy feeds the zero-point field, what is feeding energy to the dark reservoir? To answer this question, we first propose that one pair of conjugate photons constitutes one graviton, and that baryonic matter evaporates via graviton radiation. This mechanism feeds the dark reservoir of quantum potential energy. In other words, baryonic matter radiates populations of gravitons which are absorbed by the dark reservoir of quantum potential energy, via the zero-point field interface. General relativity interprets this absorption as space-time curvature. Hence, the mechanism we have described is isomorphic to general relativity. However, As one might expect, the store of gravitons within matter is finite. This means that all matter possesses a minimum gravitational lifetime. But don't worry, we'll cover this in a later slide. The important takeaways from this illustration are: 1. All matter acts as an energy source. 2. All matter evaporates via graviton radiation. 3. The gravitons radiated by matter are absorbed by the dark reservoir of quantum potential energy, via the zero-point field interface. This means that the dark reservoir of quantum potential energy acts as an energy sink. 4. The zero-point field interface is a bidirectional information layer, allowing gravitons to enter the dark reservoir of quantum potential energy, but also acting as a pressure release valve which we perceive as the Casimir effect. To ensure that the dark reservoir of quantum potential energy inflates very gradually, the zero-point field releases energy back into the physical universe to drive the experimentally observed accelerated cosmological expansion. Now that we have these fundamental concepts in place, we're in a position to start doing some calculations. So, let's move forward. In this slide, we commence the derivation process to determine the photon mass energy threshold. This is the maximum theoretical value for the mass energy of a single photon. However, before we can determine what the photon mass energy threshold might be, we first need to derive the maximum permissible mass energy of a population of photons at the harmonic cutoff mode, which is consistent with our model of the quantum vacuum. We achieve this in 7 simple steps, as shown. The key takeaways from this slide are: Step 5. The average Poynting vector power flow to the dark reservoir at each harmonic mode. Step 6. The average energy absorbed by the dark reservoir at each harmonic mode. And Step 7. The maximum mass energy at the harmonic cutoff mode of a conjugate photon population pair. Please don't forget, one conjugate photon population pair is, by our definition, a graviton. This is important, so please keep this in mind as we move forward. In this slide, we derive an important amplitude spectrum summing simplification in 3 steps. In the first step, we see that the expression in the red box denotes the summation of all odd modes across both sides of a harmonic spectrum, symmetrical about the 0th mode, obeying the Fourier sequence shown. The second step is to relate the red box to the expression in the blue box. However, the expression in the blue box denotes the summation of all odd and even modes on the right-hand side of a harmonic spectrum, that is, positive integers only, following the sequence indicated. The third step is a standard mathematical simplification of a sequence which is neither arithmetic, nor geometric. That is, neither the difference nor the ratio between terms is constant. Hence, there is no common difference nor common ratio. Thus, an alternative approach is required. This is achieved by the expression in the purple box, whereby the sum of the amplitude spectrum is expressed in terms of the harmonic cutoff mode. This is important because it simplifies the computational process, and yields a convenient solution with vanishing error, as we will see going forward. This is the final phase of the threshold derivation. The first thing we're going to do is apply the key result from the previous slide. Since we have defined one graviton as being a conjugate pair of photons, then the ratio of a population of gravitons to a population of photons is 1/2. Hence, the ratio of graviton mass to photon mass is given by the equation shown. If we solve for photon mass and execute the appropriate substitutions, we obtain a generalized expression for mass energy threshold, relating to a population of photons. We must stress, the generalized solution applies to a population of photons, not single photons. Please keep this in mind. Thus far, we have derived a generalized solution, but now we must become very much more specific. Now it's time to investigate and decide which fundamental particle can be utilized to calculate the threshold value of photon mass energy. The obvious answer is the electron, but we should be a little more rigorous. Let's look at the electron, proton and neutron. As expected, we see that the electron provides the best solution because it has the lowest value. Thus, by executing the appropriate substitutions, we can form an expression for the photon mass energy threshold based upon the electron. The photon mass energy threshold value we have calculated, denotes the total mass of a population of photons being absorbed by the dark reservoir at the classical electron radius, due to graviton radiation and the evaporation of mass. Hence, it is an upper mass energy limit, but how does it compare to authoritative sources? Let's have a look. In 2005, Storti published a photon mass energy threshold value, in favorable agreement with the 2004 particle data group boundary value based upon experimental observation. At the time of the Storti determination in 2005, the 2004 particle data group result was encouraging, but how does it compare to the 2022 particle data group estimate? We can see, many years after the 2004 particle data group estimate, that their boundary value has not significantly changed, remaining in favorable agreement with the 2005 Storti value. Therefore, we are now well positioned to advance our estimate to the next level. That is, the mass energy of a single photon and graviton. The first step in the final solution is to determine the photon population entering the dark reservoir of quantum potential energy at the classical electron radius. This is a simple matter of computing the ratio of single photon energy to photon mass energy threshold. The result returned is approximately 1.8 by 10 to the 28 photons. This means that a vast amount of photons, in graviton form, are entering the dark reservoir of quantum potential energy at the classical electron radius, every 1.76 nanoseconds. From this result, it is now a very easy matter of calculating the mass energy of the photon and graviton, as shown. However, it should be stressed that these results require the nature of the photon to be particulate, not wave-like. If the mass energy photon result is converted to frequency, the associated wavelength would be larger than the observable universe. Fortunately, photon-wave-particle duality can be explained by a wave comprising of a vast number of coherently moving particulates, so no contradiction or issue exists with the results returned. In the next step, we recognize that the conditions for a single photon at the harmonic cutoff frequency is equal to the frequency of a vast population of photons at the classical electron radius. Thus, it becomes trivially simple to calculate the size of the photon and graviton, as executed. The results presented are expressed in multiples of the Planck length, and they are astonishing. The fact that we derive a value for photon diameter, being within approximately 15% of the theoretical Planck limit, is once again astonishing, and cannot be overstated. It seems inconceivable that this result could simply be a coincidence. Let's now do a review of our key achievements. In summary, we have derived the mass energy and zero-point field equilibrium radius of the photon. Subsequently, we theorize that our value would coincide with its root mean square charge radius if it is ever experimentally confirmed. Moreover, as a consequence of our definition of one graviton comprises of one conjugate photon pair, we're also able to define its mass energy and zero-point field equilibrium radius. In addition, and quite remarkably, we derive a photon diameter of almost exactly Planck length. This result fits with theoretical expectation and is extremely impressive. Our results emphasize two possible interpretations. The first is that our value of photon diameter represents a physical limit. It suggests that the Planck length, as historically derived, is a reasonable approximation to an actual physical limit. However, the second interpretation suggests that the historical derivation of the Planck length is incomplete. It lacks an experimental relationship function and therefore, is non-physical. However, originally in 2006, Storti derived an experimental relationship function for the Planck length in the text titled, Quinta Essentia Part 3. The link to the updated 2011 revision is cited herein, as shown. And finally, as we promised earlier, the minimum gravitational lifetime of matter is given by the equation shown in the top right-hand corner of your screen. However, we prefer to apply the term starving matter because our equation refers to matter which is radiating gravitons, but does not receive any gravitons from other sources.